So far, we've already discussed expressions and statements, as well as compound statements, a sequence of statements treated as a block of code that can appear anywhere a single statement can appear. But what if you could give one of these compound statements a name, and call it by name in various places, rather than having to repeat the code? That's what functions are, a named sequence of statements. Not only that, but a function can accept arguments and return a result, making it somewhat generic and reusable. Useful programs are often made up of hundreds and sometimes thousands of functions. Hiding statements inside functions has many benefits. It can help to make it clear what code is doing. It makes it easier to test your programs. You can test a single function in isolation and then rely on it in various other parts of your program without worrying that it might be wrong or different copies of some algorithm might accidentally introduce inconsistency. This function is called a function definition. It includes a return type, in this case int, a name, Celsius to Fahrenheit, and a list of parameters in parentheses. Finally, it includes a function body. Every time you call this function, it's as if you had inserted this function body as a compound statement. But the code only appears in one place, making it much easier to maintain and test, and making the rest of your program simpler because it doesn't have to be complicated by all of these details. This also reduces code size, as code isn't repeated in many places. Reducing code size tends to have a big impact on program performance. Conversely, small functions are often inlined by the compiler, meaning that the compiler will actually duplicate the code if it thinks that there is a good performance benefit of doing so. As with global variables, all a particular source file needs in order to use a function is a function declaration, and these are typically provided in header files. This function declaration is exactly the same as the function definition, except that the function body is replaced by a semicolon, in effect hiding the implementation. The implementation, or function definition, can then be included in a separate source file and compiled separately. Indeed, this is often the case. In this example, and indeed in all cases, C passes arguments to functions by value. This means that if you have a local variable and then call a function passing it as a parameter, the act of calling that function makes a copy of that variable for the function. The function sees the copy rather than the original local variable. In effect, the function has its own copy, which is a local variable to that function. This is even the case for pointers. In that case, the function gets a copy of the pointer, but obviously not a copy of the object being pointed to. The other incredibly useful feature is the ability to create pointers to functions. This provides a form of extensibility for libraries by reducing the dependency among the different parts of a program. This becomes essential as a program grows in size and complexity. The syntax for function pointers can be a bit cumbersome. Fortunately, you can use a typedef to define pointer types for certain function signatures. Using a typedef then makes it simple to create function pointer variables. Although C provides only a small handful of data types, you can combine them in different ways using structures, sometimes called records in other languages, to produce complex data types for any purpose you can imagine. This is a structured declaration. It declares a collection of variables as a single structure that can be created, pointed to, copied, and referred to conveniently and easily. Unlike in C++, the names of structures are declared in a separate namespace in C. This means that you cannot simply define a variable like this, as the compiler will not know what color is. You need to prefix the name of the structure with a struct keyword to tell the compiler that the type is actually a structure. This does, however, quickly become tedious. A simple solution is to wrap the structure declaration in a typedef. This not only introduces the name into the global namespace, but works equally well with C and C++. A color variable can now be created simply and portably. Using structures is quite natural, and you can quickly realize the benefit of having such a construct. Initializing a structure variable is done in much the same way as arrays with an initializer list. In this case, each value fills in the value of subsequent members of the structure rather than elements of an array. Although the example on the previous slide had members of the same type, you can obviously create members of disparate types. You can also nest structures. Given a color variable, an object, I can access its members using a period known as the object member selection operator. I can just as easily create an array of structures. Naturally, the array variable can initialize a color pointer, which then points to the first color in the array. The compiler's pointer arithmetic adjusts pointer values in units of the array's element size. So the next pointer in this case will actually be 16 bytes ahead of the first pointer, assuming 4-byte floats and default padding rules. Finally, member access through a pointer is just as easy using the pointer member selection operator. For this final demo, we're going to take what we have learned about C and do something useful and a bit more realistic. Let's combine what we have learned about expressions and statements, functions, structures, and pointers, and design a simple, singly linked list, a container that can act as a queue for arbitrary program data. C is often used for writing embedded system software with severe memory constraints. A good rule of thumb when designing container and other algorithms for such environments is not to assume anything about memory management. Don't assume you can allocate memory. Don't assume your functions can even fail. Keep things simple and keep your assumptions to a minimum, and you'll produce useful and reusable code. A linked list is typically based on the idea that each element in the list contains a pointer to the next element. Let's start by declaring a structure, then, to represent such a linked element. In this case, we cannot simply wrap the struct in a type diff, since the structure first needs to be declared with a reference to itself. Only then can we use a type diff as a convenience to bring its name into the global namespace. Now we'll declare a structure to represent the list as a whole. The list thus simply stores a pointer to the first element as well as the last element. This will allow us to efficiently pop elements off the front of the list and push elements onto the back of the list in constant time. And that's all we need in terms of structure. Now, rather than having our program manipulate these structures directly, we'll wrap up this logic in a set of functions. First, we'll need a function to initialize a list to some well-known state to represent an empty list. The list_init function takes a pointer to a list object as a parameter. It then uses the member selection operator to set the first and last element pointers to 0. This signals to the remaining list functions that the list is empty. It's often helpful to be able to quickly determine whether a particular list is empty, so let's add a function to express that question. The list_empty function again takes a pointer to a list object as a parameter, and it simply compares the first element pointer with 0, indicating that the list is empty. The return type is bool, and we'll again use the bool typedef. Next, we'll add some functions to walk the list of elements. First up, we can add a list begin function to return a pointer to the first element. Pretty simple. It just returns the pointer to the first element, stored in the container. Next is the function that returns the next element, an increment of sorts. Unlike the previous functions, this one doesn't need the list itself as a parameter. It simply takes a pointer to an element and returns the next element. Now all we need is a function to push elements onto the back of the list and another to pop them from the front. This is where it gets a little trickier. We'll start with the list pushback function, which needs to accept both a list and an element. The thing to remember at this point is that the act of pushing an element onto the back of the list is different depending on whether or not the list is empty. We can express this with an if statement. Now we can more easily fill in the appropriate behavior. If the list is empty, then the newly added element is both the first and the last element of the list. On the other hand, if the list is not empty, then we first need to update the last element to point to the new element as its next element, and then set the list's last pointer to point to the new element. Finally, let's not assume that the caller knows anything about the list's implementation, and set the element's next pointer to 0 so that it properly marks the end of the list for safe iteration. And that's it for the pushback function. Now for the pop front function. This function will assume that the list points to at least one element. We can declare it as follows. As you can see, it returns a pointer to a list element, given a pointer to the list container. The pop front function needs to temporarily store a pointer to the first element. It needs to do then some housekeeping, and then return that temporary pointer. This housekeeping involves updating the list's first element pointer to point to the next element. It doesn't matter if there isn't a next element, since it will be 0 and will simply result in an empty list as you'd expect. Finally, we can return the popped element. And that's it. We should now have a working singly linked list. Of course, you have learned the essentials of the language. You have everything you need to start using C to write useful programs for any platform. But this is just the start. The best thing for you to do at this point is to start writing code, lots of it. Experiment, discover, build, break the rules, play with different libraries. Learn about the different platforms that you can target with your new skills. Notably, get familiar with the C Standard Library, a large library of functions and other definitions available on virtually all environments, providing a great many useful facilities and building blocks to help you build powerful and robust programs quickly and effectively. If you haven't done so already, I encourage you to learn C++. It is a great complement and provides many useful abstractions to augment the C programmer's tool chest.